Hello, good afternoon, good morning, good evening, depending on where in the world you are listening to us from. Welcome to this webinar, which is entitled Oil and Gas Methane Emissions and the Environmental Case for Natural Gas. We're very pleased that this webinar seems to generate a lot of interest. This is part of a series of webinars that we are doing on this year's World Energy Outlook. Most of the webinars are taking place after the launches of the respective analysis. And this one is a little distinctive in that we are basing this afternoon's discussion on a preview of some findings for the new Outlook. Thus far, we have only released a commentary which is available on the IEA website, but there will be additional material appearing on the 14th of November when we release the full World Energy Outlook. A couple of introductions. My name is Tim Gould. I am the head of division for the energy supply work on the World Energy Outlook. Together with my colleague Laura Cozzi, who heads the energy demand division. This is the team that puts together the annual outlook. For those of you who are not familiar, this is scenario-based analysis that looks ahead to 2040 with analysis by fuel, country, technology, on the outlook for energy. However, the voice that you'll be hearing most this afternoon is Dr. Christophe McGlade. He is working in the World Energy Outlook team, and he has been leading the analysis on this afternoon's topics. The format for today, we won't keep you more than 1 hour, but we will start with a presentation of the findings on this topic for around 25 to 30 minutes, and then we'll have the opportunity to take your questions. Some of you have submitted some questions in advance. Others, you can do so as we go along via the browser for this webinar. We'll try to cover as many of these questions as we can before our time is up, but we may not be able to cover them all, in which case we will be happy to follow up by email as necessary. So please do send your questions in. We'll be very interested to hear from you. Before passing the floor to Christophe, a bit of context. As I mentioned, the WEO covers all fuels and technologies, including energy efficiency. And every year we have a fuel focus in the World Energy Outlook. In the WEO 2016, that focus was on renewables, and this year it's on natural gas. And as I mentioned, all of the material will be launched as part of the World Energy Outlook on the 14th of November. So the fuel focus on natural gas covers all aspects of the outlook. It's a detailed look by sector and region at the prospects for gas in different scenarios to 2040. In different sectors, gas might be competing against coal. It might be competing in some ways, but also facilitating the rise of renewables. It's also affected by the increasing policy accent on energy efficiency. So those are the sorts of areas that we would be looking at. Another aspect of the work is to understand the new gas market order that is emerging, spurred by the rise of LNG, a more flexible, a more liquid, globalized market. And we're interested to understand the implications of that for investment and gas security. But we're also very keen to address an issue, which is the role of gas in a changing energy world, its role in the multiple energy transitions that we are observing worldwide. And when we think about the long-term role of gas, one area that becomes clear very quickly is that this is closely linked to the ability of gas to help address environmental problems, whether that's climate change or concerns about air quality. This ability of gas to replace more polluting fuels has been very much part of the dynamic in the United States in recent years, also in the UK. And if you look at the numbers for LNG imports to China, for example, this year, you can see how concerns about urban air quality are spurring quite a big increase in gas demand there as well. In assessing this environmental contribution of gas, some things are very clear. There's very little doubt, for example, about the combustion emissions of gas relative to other fossil fuels. And as Christophe will discuss in a minute, these show some clear advantages for gas. However, there's much less consensus over the level of direct methane emissions that can occur whether by accident or design, on the path from oil or gas production to final consumer. And in our view, this is a critical issue for the long-term natural gas outlook, as methane is a potent greenhouse gas. And so the uncertainty over the level of methane emitted to the atmosphere raises questions about the extent of the climate benefits that gas can bring. So one of our forthcoming World Energy Outlook 2017 analysis was to investigate the sources of this uncertainty and explore what actions can be taken to reduce emissions. And that's what Chris is going to discuss in more detail now.
Thank you, Tim. So, as Tim mentioned, the emissions that arise from natural gas combustion show some clear advantages over the combustible fuels. And whenever we talk about emissions here, this includes the three main pollutants that are responsible for the most widespread impact of air pollution. It includes fine particulate matter, sulfur oxides, most notably sulfur dioxide, and nitrogen oxides. Controlled burning of natural gas releases very few particulate emissions into the air, and in global terms, it's very much the combustion of wood and other solid fuels that are responsible for more than half of particulate emissions. In terms of sulfur dioxide, which is a key cause of respiratory illnesses and a precursor for acid rain, coal is responsible for more than half of emissions globally, followed by emissions from oil. In both of these cases, the contribution of natural gas towards pollutant emissions are relatively low. Onwever, for NOx, for nitrogen oxide, the combustion of gas does produce some NOx, but even here, gas is responsible for only around about 10% of global energy-related NOx emissions. Finally, as we'll all be aware, gas does result in some level of CO2 emissions, carbon dioxide emissions when it's combusted, but per unit of energy provided, the emissions from natural gas are around 40% lower than for coal, and they're about 20% lower than for oil. All of these factors mean that gas is a relatively clean fuel compared to other fossil fuels. But as Tim mentioned, a major potential issue for gas is the fact that it is predominantly methane, and since methane is a major greenhouse gas, if there are any leaks during the production, transport, consumption of gas, this can negate some or maybe even all of the climate advantages that natural gas can provide. Before looking into this issue of oil and gas related methane emissions in more detail, it's worth taking one step back and examining the issue more generally. Each year, there's around about 570 million tons of methane emissions, both from natural sources and from anthropogenic or man-made sources. However, there's a very high degree of uncertainty over this number, particularly whenever we try to attribute methane emissions to any specific source. Nevertheless, man-made sources are estimated or are likely to be responsible for the majority of these 570 million tons of emissions. And it is these that are a particularly large concern for the global climate. Agriculture is the single largest emitting sector, but closely follows the energy sector, both responsible for about a quarter of total global methane emissions. And just to note that whenever we talk about energy sector emissions here, we include emissions from the production and consumption of coal, oil, gas, as well as biofuels. And just to note that methane exists in the atmosphere for around about 12 years after it's emitted, but the rise in man-made sources of methane mean that the atmospheric concentration of methane today is around about 2.5 times the level it was in pre-industrial times. And methane absorbs a lot more heat than carbon dioxide, for example, when it is in the atmosphere. And so currently, methane is the second largest greenhouse gas after carbon dioxide. So moving now to focus on the methane emissions from oil and gas production. As part of the analysis we carried out for the 2017 World Energy Outlook, we generated new estimates for the level of methane emissions that we believe comes from oil and gas operations. The method that we generate these estimates relied first on generating country-specific and production or segment-specific emission intensities. And then secondly, we applied these emissions intensities to oil and gas production and consumption data on a country-by-country basis. To generate these emission intensities, our starting point was the 2017 US Environmental Protection Agency greenhouse gas inventory, as the methane emissions that are estimated to come from the United States have been analyzed more fully than those in any other countries, And also an awful lot of data is available for the United States, which isn't necessarily the case in a number of other countries. And we supplemented these US data with a range of other sources, including an extensive survey we undertook of major oil and gas producing companies and a number of companies that use natural gas. Then for the estimates outside of the United States, we then scaled these US emissions intensities. And this scaling was based upon a range of auxiliary country-specific data, such as the age of infrastructure in each country, the types of operator that exist within each country, the extent of the oil and gas pipeline networks, and also the strength of regulation and oversight. And these auxiliary data were particularly important to scale the emissions intensities from the United States to countries in Africa, the Middle East, and Asia, for which there's almost no direct measured or reported data. So looking at the figures shown here, we estimate that in 2015, methane emissions from oil and gas operations around the world were just over 75 million tons globally. Eurasia, incorporating Russia and the Caspian region, and the Middle East are the two largest emitting regions, followed by North America, which is responsible for just under 20% of oil and gas methane emissions. When we look at the split of emissions from between oil and natural gas, just over half of the 76 million tons that we estimate comes from natural gas operations, so around about 42 million tons annually. And this includes the upstream sector, processing of natural gas, as well as the downstream sector, which we say incorporates the transmission and distribution of natural gas to end use consumers. And also just to note that there's a contribution to methane emissions from flaring. A flare, generally speaking, is designed to combust natural gas that cannot be marketed in any other way. But in any flare, there can be a small proportion that's not fully burnt, and so this is released to the atmosphere as methane. And this source of emissions is responsible for just under 5% of the global total. So as mentioned, just around about half of our estimate of total oil and gas methane emissions comes from natural gas operations. And to come back to the question we posed at the beginning of the presentation, what does this mean for the overall climate benefits given by natural gas? One frequent complaint made against natural gas is that the methane emissions along the value chain are so high that when these are fully taken into account, the life cycle emissions, the life cycle greenhouse gas emissions intensity of natural gas can be worse than coal. So within our analysis, we carried out this comparison, and to do so, there's a number of different elements that need to be taken into account. First of all is the relative combustion, CO2 combustion emissions of gas relative to coal. And as mentioned already, gas has clear benefits on that metric. And also we need to take into account the methane emissions that come from natural gas operations, as well as the methane emissions from coal production. Another key variable as well, we're interested in whether it is electricity that we're interested in measuring the emission intensity over, or whether it's heat. The conversion of natural gas into electricity tends to have a higher efficiency than in coal power plants. And so the life cycle emissions intensity for gas are lower if we are looking or are interested in electricity than if we're interested in heat. And finally, one of the key assumptions is how do we convert a ton of methane that's emitted into a ton of CO2 equivalent. And on this point, it's very common to rely upon what's called the global warming potential. As mentioned, methane traps much more heat than carbon dioxide per unit of mass while it's in the atmosphere, but it stays there for a much shorter period of time. And unfortunately, these two things mean that it's not particularly simple to convert a simple conversion between a ton of methane and a ton of CO2. And most notably, the conversion factor depends on what time frame is considered of most of interest. So for example, if we're looking at the impact of methane over a 20-year time frame, 1 ton of methane is broadly equivalent to around about 84 to 87 tons of CO2. But over a 100-year time frame, 1 ton of methane is equivalent to around about 30, ranging between about 28 and 36 tons of CO2. This figure takes all of these various factors into account, including the most recent global warming potential estimates given by the Intergovernmental Panel on Climate Change. And just to explain this figure in a bit more detail, if we're in the top right-hand side of the figure, then that would mean that coal on a life cycle emissions intensity basis is better than natural gas. If we're in the grey band towards the middle, then natural gas is better than coal for electricity, but not necessarily for heat, because of the differences in conversion efficiency. And if we're in the purple area, then gas is better than coal. So considering the relative greenhouse gas intensity of the two fuels over a 100-year time frame, the light blue band shown there, if the amount of gas that is leaked during its production and transport is below 5.5% of the gas that is produced, then gas has a lower life cycle emissions intensity than coal. Over a 20-year time frame, the darker band, then the leakage rate of the emission intensity must be below 3% for natural gas to be cleaner than coal. Our estimate of 42 million tons coming from the natural gas value chain translates, broadly speaking, into a global average leakage rate of 1.7% globally. Therefore, as a global average, gas is better than coal, regardless of the time frame that is considered. However, it's very important to bear in mind two key caveats to this finding. First of all, just because the global average is below the break-even point, this doesn't necessarily mean that gas from all countries is currently better than coal. Secondly, even if natural gas is always better than coal, simply comparing natural gas to the most emissions-intensive fuel is somewhat setting the bar too low. If deep greenhouse gas emissions reductions are to be realized in the global energy system, it's not sufficient simply for natural gas to result in fewer emissions than coal. The emission intensity of natural gas needs to fall to as low level as is practicable. So what can be done about to realize reductions in global oil and gas methane emissions? To answer this question, we constructed a number of marginal abatement cost curves for methane emissions reductions. These tools have been used before to examine the technical potential and costs of reducing methane emissions in countries in North America, but in our analysis we extended this beyond North America so that for the first time we can look at the global picture of the emissions reductions and monetary costs or savings that can result from the use of different abatement options. Marginal abatement cost curves describe the reductions that can be achieved using different technologies by moving from the left-hand side towards the right-hand side on the horizontal axis, at different costs of savings by moving up or down the vertical axis. And one really important aspect of these curves is that since natural gas is a valuable product, the methane that is recovered can often be sold. And this means that deploying certain abatement technologies or mitigation options can result in overall savings if the value received for the methane that is sold is greater than the cost of the technology necessary to bring about that abatement. And just to give a bit of detail on how we constructed these curves, we disaggregated the emission sources for each country into around about 90 different equipment-specific emission sources from across the whole oil and natural gas value chains. We then estimated around about 50 known abatement technology options to mitigate these emissions from the different equipment-specific emission sources. And each of these technologies has different capital and operating costs, different lifetimes, different emission reductions potentials, and different applicability factors. And so the cost assumptions, which vary between regions and also over time, mean that different regions will have different costs for deploying the same technology. But it's also important to note that the prices that are received for the natural gas that is saved will also vary between different countries and between different regions, and will also, again, vary over time. And it's important to note that we examined this issue, the issue of trying to abate methane emissions from oil and gas operations from a global and societal perspective. And so that we assume that any methane that is recovered and can be resold, regardless of whatever contractual arrangements exist between different companies and or different values that are attached to that gas, means that gas can be sold, and that therefore there is a saving from deploying that technology. So looking at now at the figure on a global basis of the current 76 million tons of methane emissions that we estimate come from oil and gas operations, we estimate that it's technically possible to avoid around about 3/4, or just under 60 million tons of these emissions. The remaining emissions are estimated not to be technically avoidable. But very importantly, around about 40 to 50% of the methane emissions, around about 38 million tons, could be avoided just by using technologies and approaches that would pay for themselves to the captured methane that can then be sold. These are all of the measures which are below the horizontal axis shown there. In terms of the split by country, the regions that have the highest wellhead natural gas prices have the greatest proportion of emissions that can be mitigated at zero or negative overall costs. So, for example, in many developing Asian countries, the price that can be obtained for methane that's recovered is relatively high. In addition, labor costs are relatively low, and that means that, broadly speaking, the proportion of methane emissions coming from developing Asian countries that can be mitigated at negative or zero cost is higher than in many other countries. However, even in those regions with lower wellhead prices, there are still a number of positive net present value measures that can be deployed. To give one example, in North America, around about 20% of the total oil and gas related methane emissions could be eliminated using technologies with negative or no overall costs. Nevertheless, it's even in these regions where a smaller percentage of reductions are possible at zero or negative costs, reducing oil and gas methane emissions remains a very cost-efficient way of reducing total greenhouse gas emissions compared with many other mitigation strategies for example, CO2 emissions. So far, this has very much been a discussion of the situation as we see it today, but this is clearly going to evolve as we move forwards. And one of the key aspects of the 2017 World Energy Outlook is to look at what will happen under different scenarios looking forwards. And in our central new policy scenario, oil and gas production increases up to 2040. And so in the absence of any measures to reduce methane emissions from these operations, methane emissions will also continue to rise. So by 2040, oil and gas methane emissions would have risen from around about 75 million tons to over 105 million tons by 2040. However, currently there's a number of policies around the world in place to reduce methane emissions, and also given that a large proportion of the abatement options actually make money, it's reasonable to assume that a number of these measures start to be gradually adopted over the course of the new policy scenario. And so in the new policy scenario, we assume that any measures that consistently have positive net present values will be fully deployed by around about 2040. And as a result, oil and gas methane emissions would then fall to around about 50 million tons globally. Just focusing on the natural gas side of things momentarily, methane emissions from gas in 2040 would be around about 35 million tons. But because natural gas production is around about 50% higher than it is today, this means that the emissions intensity of natural gas in 2040 would be just under 1% globally, compared to the 1.7% that we estimate exists today. So the final question to ask is, what's the impact of all of these reductions in terms of the benefit to the climate? The most common approach to estimate the impact of reducing methane emissions on the climate is, again, to use the global warming potentials that were discussed before to convert the tons of methane saved into tons of CO2 equivalent saved. However, for a wide variety of reasons, we wanted to avoid this, and we used a different approach within the World Energy Outlook. What we did was to use a climate model called MAGIC to estimate what the average global surface temperature rise in 2100 under the new policy scenario would be. First of all, if we don't do anything on methane emissions, so if oil and gas methane emissions rise up to 105 million tons, as shown, and then what the temperature rise in 2100 would be if we did incorporate the abatement measures shown. And running these numbers through the model, what we found was that the temperature difference between these two cases is around about 0.07 degrees Celsius. And this sounds very tiny, very small, but in climate terms, it's actually a very, very large number. And the best way to view this is to estimate the equivalent level of cumulative CO2 emissions that would need to be emitted or to be avoided to give the same temperature difference between these two scenarios. So to reduce the temperature rise in 2100 by 0.07 degrees Celsius by reducing just CO2 emissions rather than reducing methane emissions would require emitting around about 160 billion fewer tons of CO2 over the remainder of the century. And to put this into context, this is broadly equivalent to the CO2 emissions that would be saved by immediately shutting all of the existing coal-fired power plants in China. In other words, tackling oil and gas methane simply by using technologies that would end up paying for themselves over the long run would have the same climate benefit as shutting down every single one of China's coal power plants that is operational today. And with that, I'll hand it back to Tim for the conclusions.
Thank you very much, Christoph. I will just run through these very quickly, and in fact, I won't comment on them at all, but I will just leave them on the screen, and probably make some more general observations in these concluding remarks. As many of you will know, in the World Energy Outlook, we have multiple scenarios that describe different possible pathways for global energy. But they have a few things in common. The contribution of gas to meeting global energy needs grows in all of them. So when we look at how these scenarios differ, the pace of growth that we project for natural gas in these various scenarios is determined by a range of factors. One of them, which is something that we're going to look at in some detail in the forthcoming analysis, is really the affordability of gas relative to other fuels and technologies. Clearly, the policies that governments put in place will likewise play a very significant role. And also the factor I mentioned at the start, so the impact of this increasingly liquid and globalized gas market on investment and security of supply. But the conclusion that we'd like to leave with you from this analysis is that, in our view, the pace at which gas grows in the future will also depend on the industry demonstrating credibly that methane emissions from oil and gas operations are being minimized. I think now we will move on to questions. Many thanks to those of you who have already sent things in. Before we do so, I can clarify already one point raised by Vladimir Tuzov. The presentation today will be available on our website, and I believe we would also be including a recording of this webinar alongside that. I'd also like to just clarify the material that we're going to be releasing on the 14th of November. So that's the World Energy Outlook itself, including the chapter from which today's webinar was drawn. In addition, since not everything can go in the published book, we will put some additional material on our website on aspects of the methodology. So two questions in particular where we would like to describe the approach. One is how we arrived at the figure of 76 million tons of estimated emissions from oil and gas operations, and how we derived the MAC curve. So I can see a number of quite technical questions coming up on the feed. We may steer clear for some of them now on the basis that would become clear once this material is available. A final observation, which really speaks to one of the questions that we received, which is about uncertainty. So all of the estimates here are subject to a wide range of uncertainty. What we have presented today is our best understanding of a complex issue, but this is also an area where data are scarce, particularly outside the United States. We very much welcome the various initiatives underway to improve the quality of the data and the availability of that data. And that is an area that we will be following very closely as and when we return to this issue in subsequent World Energy Outlooks. And actually, I would like to start with a question on that point. This came in from Melidios. What is your level of confidence over the numbers that you're reporting in view of the recognized data gaps that exist?
So I think it's fair to say that, as I mentioned, the emissions data that exists for the United States is the best that there is out there. There's been a number of academic studies that have been carried out in the United States looking at all aspects of the natural gas and oil value chains. And this has led to a huge advance in the understanding that exists. Very importantly, because the data for all of these studies was made available publicly. There are a number of other countries which have mentioned to us that their data is available and that they measure these things in a careful and robust way. However, it can sometimes be difficult to disentangle all of the different estimation methods that have been used And if the data is not made available publicly, then it can be very difficult to audit. And this is one of the key issues that exists for estimating oil and gas methane emissions around the world. However, I would just say at this stage that the key issue that we kept coming up against during the course of the study was the lack of direct measurements that have been taking place outside of North America around the world. In some countries, we can be more confident than others because they have a robust and a clear method for estimating their methane emissions. In some parts of the world, there's almost no data that exists at all. The 570 million tons of total methane emissions that are estimated to exist, there is an uncertainty bound on that, but that uncertainty bound grows and grows over time as you try to attribute the 570 million tons to more specific sources. And in particular, it grows as you try to associate those emissions to individual countries. So the level of confidence is this is the best numbers that we could come up with given the data and information that was available. However, this is by no means the final word on the issue, and we certainly hope that more information will become available over the coming years. And indeed, we're aware that there are a number of studies underway to improve the measurements and estimates of data in parts of the world outside of North America.
Thanks, Christoph. Wanted to come back to when you talked about with the MAC curve, the emissions that can be abated at no net cost. If these are indeed opportunities to make money, essentially, because the value of the methane is greater than the cost of the abatement technology, then why are these investments not going ahead?
So this is something that clearly perplexed us whenever we first developed these MAC curves, and really the difficulty is that there's no single explanation as to why these measures haven't been adopted. The reasons really vary from country to country, but the possible causes or reasons for this that we thought seemed reasonable was, first of all, that there's a lack of awareness or understanding of the level of emissions that there currently are around the world. Secondly, that there's a lack of awareness of the cost effectiveness of abating these emissions. But then within companies, for example, there's often a heated battle for capital. And this means that whenever you're weighing, should we invest in a methane abatement opportunity or spend the money on something else, it means that the methane abatement option might not necessarily come at the top of the pile in terms of the payback period or the rate of return that you would receive from implementing that measure. And there's also, which is a very important issue, is the possibility of split incentives between the people that own the gas and the people that would have to carry out the abatement measures. So, for example, in some countries, the owner of the equipment that would need to make the investment doesn't actually own the gas themselves, and so there's very little incentive for them to actually bring about that capital investment and avoid that methane from being emitted. In other countries, there's distortionary fossil fuel subsidies, for example, that mean that the companies that produce the oil and gas don't necessarily see the full value of the methane that's emitted. And just to come back to the first point there on the lack of awareness potentially that exists in different parts of the world, this is really where we see the role of partnerships between international and national companies coming into its strength. If in joint ventures, for example, if the international companies who are broadly speaking and generally speaking very well aware of this issue and are doing their best to reduce their methane emissions, can help their partners bring about reductions, this could really lead to a greater understanding and a greater reduction in emissions around the world.
So we've had a couple of questions on the chart which compares the greenhouse gas emissions intensity of gas versus coal. And one of the lines on there was taking into account the different conversion efficiencies of gas and coal for generating electricity. The question came in from Fiji George and Benjamin Israel about, so what efficiencies what technologies are we looking at there? What efficiency for power plants did you assume to make this comparison?
So for the coal power plants, we assumed a new plant that is installed around the world, and broadly speaking, it has an efficiency of around about 40 to 45% in terms of the amount of coal that's consumed per electricity generated, whereas for a combined cycle and gas turbine, it's closer to around about 55 to 60%. And so if all else being equal, that would mean that per unit of electricity that's generated, gas would be better than coal. However, on top of that, as you mentioned, the combustion emissions of CO2 are also lower for natural gas than for coal. And so these two factors work in conjunction.
On the same slide, there's a few questions about the 1.7% emission intensity or leakage rate. That is just for the gas value chain. So it covers the 42 million tons out of the total 76 million tons estimate. What about the rest? What about the 34 million tons for oil? Where do these come from? And what about the things that the methane released from the energy sector, but beyond oil and gas? So what about coal, bioenergy? Why not focus on reducing emissions from these sources?
So taking oil emissions, first of all, in terms of where these come from, it's the first thing to note is that oil methane emissions almost exclusively take place in the upstream sector, that is in discrete facilities. And the possible sources for oil methane emissions include things like pneumatic controllers and chemical injection pumps, storage tanks, and then also from what's called cold venting, where any gas that is small quantities of gas that are produced alongside the oil are simply vented into the atmosphere rather than, for example, sending that gas to market or re-injecting that gas into the ground, or indeed just flaring that gas. And clearly then it's given that most of the, or nearly all of the oil methane emissions come from the upstream sector, this is because once the oil has been processed, there's not a huge amount of methane that is in that left in the oil as it's transported. Whereas for natural gas itself, after it's processed, you still have in transmission and distribution pipelines that gas is, if any of the gas is leaked, that will mean that you will get methane emissions in the atmosphere. And so what this means, because you have more discrete sources of oil methane emissions, generally speaking, that means it's slightly easier to tackle oil methane emissions than it is for natural gas. Because during the transport for natural gas, these can occur over very long and widespread geographic areas along a transmission pipeline, for example, which means that if you have a fugitive source, a leaky part of that pipeline, it can be difficult to detect. And therefore, you have to have programs in place to detect those emissions. And because you have to cover a large area in your leak detection program, this can add to the expense. Inspecting and repairing emission sources in upstream in a discrete facility can be a lot more time efficient. And this is reflected in the proportion of oil methane emissions that can be avoided cost effectively compared to gas. So I mentioned, roughly speaking, 40 to 50% of total methane emissions can be avoided around the world, but this is split. Around about 60% of oil methane emissions can be avoided using measures that have positive net present values, and around about 40% for natural gas. So for coal operations, since you also mentioned that, those were clearly taken into account in that figure comparing the life cycle emissions intensity of gas and coal. And we estimate there's around about 40 million tons of methane coming from coal operations. Clearly, most of these emissions, given that China is the largest producer and consumer of coal, means that China is the largest emitter of what's called coal mine methane. And there's various different ways in which this methane can occur during coal production, degasification and ventilation of underground coal mines, for example, necessary to avoid any explosions that may occur. The exposed coal seams in surface or open pit mines can cause emissions. Abandoned coal mines can be a source of emissions. And also some post-mining activities such as storage and transport can lead to emissions. And why we focused on oil and gas emissions rather than coal is that the concentration of emitted air from coal mine methane can vary quite significantly by source. So for example, wells that are drilled to gasify coal mines often produce high concentrations of methane, but the air that comes from ventilation systems has very, very low quantities of methane concentrations in the air. And these therefore mean that it can be much more difficult to abate these low concentration air sources of methane. And so there certainly is some technical potential to reduce methane emissions from coal mining. However, because we had a focus on natural gas as part of this year's WEO, because it's possible to monetize that methane, given that the natural gas is being produced anyway, this is why we focused on methane emissions from oil and gas operations.
Okay, thanks very much for that. There's been a couple of questions. I mean, we're clearly talking with the action on to reduce methane emissions about reducing the environmental footprint of natural gas. And Stefan Singer raises then the question about renewable gases. So biomethane from waste, hydrogen, which could play a role along with things like power to gas for long-term energy storage. To what extent have you considered the role of renewable gases in the outlook to 2040?
So absolutely, we consider the role that renewable gas could play in the energy system going forwards. That element of the work was not included in this presentation, but is certainly included in one of the other chapters within the World Energy Outlook that will be published in November. And we look at the potential for renewable gas around the world and the cost at which it could potentially be produced at. Similarly, we also look at hydrogen and the different ways in which hydrogen can be used in the future global energy system. For example, injecting hydrogen into natural gas streams, what percentage of the natural gas stream could be converted to hydrogen without any major changes to infrastructure, or could hydrogen become a key energy vector in of itself? All of these issues are taken into account in the analysis, and obviously they come through much more strongly in our scenarios which have a deeper reduction in greenhouse gas emissions than under, for example, the new policy scenario.
You mentioned the new policy scenario, and I'm just going to scroll back to one of your other slides, this one, because here we're showing methane emissions in the new policy scenario with and without abatement measures. And as I think you mentioned at the start of your presentation of this slide, this shows a very gradually rising trend for oil, but a significant then potential increase in gas demand in this scenario to 2040. And this raises the question, which has been picked up by a few listeners, Katie House, Antoine Simon, and Frieda Kinninger, about, I mean, this new policy scenario doesn't look from this slide like it's one that's consistent with the objectives of the Paris Agreement. And indeed, people who are familiar with the work that we've done, or the previous projections that we've done in previous editions of the Energy Outlook, you know, one of the key analytical conclusions is that if you take into account the policies that have been announced and the policies that are in place already, then indeed, you know, the emissions trend to 2040 does not show the early peak and subsequent rapid decline that is mandated by Paris. So how does this picture look then in a scenario that is consistent with Paris? I mean, I think you mentioned a scenario which is going to be a new scenario in this year's outlook, which is called the Sustainable Development Scenario. So indeed, if you are in such a scenario and you need to reach net zero emissions in the second half of this century, then are methane emissions reductions still important? I mean, how does that play into a longer term discussion?
So in the sustainable development scenario, as Tim mentioned, this has one of its key objectives is a peak in global energy sector emissions as soon as possible, followed by a rapid decline in emissions. Clearly, under this scenario, the fossil fuel that suffers to the greatest degree is coal, as coal is phased out of a number of countries. We also see a peak in oil consumption and oil production, and then a decline in that going forward. But natural gas is really the fuel that fares the best in this sustainable development scenario. So between now and 2030, natural gas consumption grows by around about 20% globally. However, I should point out at this stage that increased use of gas just by itself is far from sufficient to reach the global climate objectives in the Paris Agreement. This has to go alongside a very rapid rollout of increased deployment of renewables, of energy efficiency, of alternative vehicles, and so on and so forth. A huge number of measures are important, and if all of those are in place, that leaves a space for natural gas to form a function within the energy system. And the opportunities that exist for gas in sustainable development vary across different sectors, between different regions, depending on their status of development and the infrastructure in place, and also varies quite a lot over time. And so we can't really say in a simple way that there's a one-size-fits-all approach to natural gas and the role of natural gas in a sustainable development scenario. So, for example, the growth of natural gas consumption is most beneficial wherever it replaces more polluting fuels, in particular coal. And in some sectors, there are limits to the rate at which renewable energy options can be scaled up, and that presents an opportunity for natural gas. And also there are some parts of the energy system where it can be harder to find cost-effective zero carbon options, such as high temperature heat in industry or in marine bunker fuels. But another way in which gas helps in the energy sector transition, as envisaged in the sustainable development scenario, is that it can be a really important source of flexibility for the energy system, for the electricity system in particular. Whenever we have an increased level of renewables, solar PV and wind in the electricity sector, natural gas can really help to support the deployment of these up to very high levels. And this is really one of the key ways in which we see natural gas changing over the course of the sustainable development scenario. But I should also just finish by mentioning that there are a number of different changes that need to happen in the way that gas is produced and consumed. We have very rapid reductions in methane emissions coming from natural gas production, and also the way in which we consume natural gas starts to change, so that in a number of different sectors we have carbon capture and storage. We also have already mentioned the role of biomethane and hydrogen. And perhaps just to finish by discussing why a methane emission policy reductions, why a methane reduction policy is still important in a sustainable development scenario. We repeated the analysis that's shown on this slide for what happens to methane emissions. And broadly speaking, with the decline in oil consumption, but the rise in gas consumption, methane emissions stay around about 75 million tons between now and 2040. However, given that we're working very hard on decarbonizing the whole energy sector, we assume in the sustainable development scenario that there will also be stronger efforts to reduce methane emissions. And so we assume that by 2040, nearly all of the technically potential, all of the emissions that can be reduced technically are implemented by 2040. And this means that methane emissions are around about 75% lower than they would have been in 2040 otherwise. And repeating the analysis for what that means for the climate gives us quite a similar result, actually, what we saw in the new policy scenario. So in the new policy scenario, the difference between abating or not abating is 0.07 degrees Celsius in 2100. In the sustainable development scenario, the difference is about 0.06 degrees. And in the context of a rapidly decarbonizing energy system, this 0.06 is really, really important because it's equivalent to around about 140 billion tons of CO2.
There's another set of questions which have come in from a number of people, Marcus Recker, Nick Reilly and others, regarding the emissions intensity of different pathways to market. So did we compare the emissions intensity of LNG value chain versus pipeline deliveries versus domestic supply for different countries and regions? I think I might take that one up because the answer is that we didn't go into this in detail. It is an area, though, which we are very interested to follow up on. And so, although I think we'll probably need to finish working on this year's outlook before talking too much about the World Energy Outlook program for 2018, but that's certainly an area that we would be interested to take up the emissions intensity across the oil and gas value chains for the future. Another question came in regarding, in a sense, what's missing for some of these abatement opportunities to be taken up. Are there technology gaps? Melidros asks about new detection technologies and the state of commercialization. Can these, in a sense, be widely deployed? So what are the opportunities there in that area?
So I think for this, the key point is that whenever an oil and gas company discovers a leak, generally speaking, it can fix that leak pretty quickly. Broadly speaking, in our discussions with companies, the maximum length of time it would take between when a leak is detected and when it's fixed is around about 15 days. And the majority of the leaks can be fixed much more quickly than that. So broadly speaking, the technologies that are needed to bring about these reductions there's not that much new technology innovation required for the actual mitigation that's required. Where technology innovation is really crucial and critical is in the detection and in the measurement and in the quantification of methane emissions that exist. Currently, there's not a huge number of cheap and readily available measurement options available. So, for example, I mentioned the leak detection repair programs that are carried out by a number of companies around the world, and these are very important to reduce fugitive emissions. Wherever you have an accidental leak of methane emissions, if you have to detect that leak, and then you can repair it. And in a number of cases, the option for this leak detection is to use an infrared camera and walk around your site or your pipeline and examine to see where there might be methane emissions or there might be a leak. This is quite an expensive and well, it certainly can be an expensive way of detecting emissions. We found that a number of companies implemented leak detection repair programs and found they were very cost effective. However, over time, as you would expect, as more leaks are detected and then repaired, the payback for this program decreases over time. So in the first year, you might make money from the leak detection and repair. Second year, you might break even from it. And then in the third year, it costs you more to detect, to carry out this leak detection repair program than from the methane it saves. So really where the innovation is required is in cheap ways and quick ways of being able to detect and in potentially be able to anticipate whenever leaks might occur. So for example, if you have equipment which can start to wear out, if you can predict whenever there's a leak is likely to occur, maybe you can replace that piece of equipment slightly before it completely breaks down, so that you can avoid those emissions.
Okay, thank you very much, Christoph. We are almost out of time. I would just take a couple of questions which we can answer quite quickly. A question from Tony Edison about the way that fossil fuel subsidies discourage methane capture. That's certainly the case, and that would affect the incentives for people to take advantage of potential mitigation opportunities. That is, the distorting effect of fossil fuel subsidies on energy efficiency investment, on this issue, on a variety of other areas, is one reason why we have been tracking those subsidies closely in the World Energy Outlook, and we'll be updating our estimate for fossil fuel consumption subsidies worldwide in 2016 when we publish on the 14th of November. And another question that came in from Michael Lazarus: are we going to provide documentation to explain the 2100 temperature impact comparison? And the answer is yes. We will be putting that up on the website to accompany the release of the Outlook in a couple of weeks' time. There are additional questions on the line, but I did promise that we wouldn't take more than an hour of your time. So I think we will leave it there. And it remains only for me to thank Christoph very much for his answers today, but also his leadership on this analysis together with colleagues from the World Energy Outlook team. And to thank you all for your participation today. Those of you who have submitted questions that we haven't yet answered, we will be getting back in touch with you by email. And we look forward to continuing this conversation, but also with the launch of the new World Energy Outlook, to discussing the wide range of issues that we're looking to cover about the future outlook for natural gas. Thank you very much.